Okay, so today it's a pleasure to have Marjy Friedrichs from the Virginia Institute of Marine Science as our seminar speaker. Marjy started out with a degree in physics from Middlebury, and after that she went to Woods Hole to the MIT Woods Hole Joint Program where she got her master's degree. And then for a variety of reasons, she ended up in Old Dominion University and was a student here for getting her PhD. Marjy did her PhD work on data assimilation in coupled physical biological models, and that's not mentioned in her biography here, but I just wanted to mention it because she's one of the people that her work actually showed that how feasible it is to do data assimilation for biological data in these coupled modeling frameworks, and she deserves a lot of credit for doing that. She was also the Rachel Carson speaker at the AGU meeting last year in Washington, D.C. And if you have a chance to watch her presentation, you should do that because it was a very good one. But today she's going to talk about work she's done at VIMS, where she is currently the University Professor for Research Excellence at William and Mary, or at VIMS. And she's going to talk about the Chesapeake Bay Environmental Forecasting System. And this is a system that she and her students and postdocs have built, and she oversees the operation of this system. So Marjy, please go ahead.
Great. So yeah, thank you, Eileen, for that introduction. Yeah, I spent many years at CCPO, so it's yeah, fun to be back speaking in the seminar series. So yeah, as Eileen said, I wanted to talk today about our Chesapeake Bay Environmental Forecasting System, otherwise which we known as CBEFS. And yeah, so I have a whole slew of people to thank. First of all, NOAA for funding this in a variety of different ways for over many, many years now. And then in terms of people, I've had lots of different students work on this and collaborators throughout the years. But three folks I really want to thank are Aaron Beaver from Anchor QEA, which is a consulting company on the West Coast, and he really manages the forecasting system, make sure it's up day to day operationally. Pierre St. Laurent at VIMS, and he's just responsible for all the different modeling parts. He does everything. And Raleigh Hood at UMSES has worked with us throughout the years as well. So I wanted to note him too. So I wanted to start talking today a bit about all the different stakeholders we've been working with, as it's really their needs that have driven the development of the system. So who are the stakeholders we've been working with? So we have a whole slew of different people, and these include folks such as recreational anglers and commercial captains. They need to know the oxygen concentrations in the water. They want to know what waters might be low oxygen and hypoxic. They want to know the temperature of the waters, so because some fish like one temperature more than others. And then water clarity as well, because they want to be able to fish in clear waters, because in murky waters, the fish can't see the lure and they just won't be successful. So they use all this information to determine where they should go fishing on a day-to-day basis. We also work with the shellfish aquaculture industry. In particular, the hatchery operators, and then also managers involved with shellfish restoration. They want to know the pH of the water, saturation state, as well as salinity and temperature as well. In particular, hatchery operators need to know whether they are going to have to treat the bay intake water. If it's particularly low pH and acidic, they may need to treat that. We also work with beach managers and basically the general public, anyone who wants to go to the beach on a sunny summer day. They want to know, all these folks want to know whether the beach waters are safe. They want to know if they're going to go and find a yucky algal bloom there. They want to know if the temperature is good for swimming or whether there's going to be jellyfish. So they all use our forecasts as well. The beach managers aren't going to close a beach because of our forecasts, but they will alter the frequency by which they're measuring the water quality at the beach. So if our forecasts show that it's going to be poor water quality for and potentially bacteria or harmful algal blooms at the beach, they will go do their measurements more often during those time periods. And then I just put down power plant operators here. They've contacted us because they want to know about the jellyfish in the water. If they the It's a pretty well-known problem that power plants have. If they take intake water has jellyfish, that completely messes up their system. So they want to know about jellyfish concentrations. And then coastal resource managers, like those folks at the Chesapeake Bay program, they really want to know whether all of their nutrient reductions are working and whether chlorophyll is going down, hypoxia is going up, or oxygen concentration is going up. They're interested in water clarity as well. And finally, scientists, teachers, and students, we provide information to a lot of different researchers that are going out on the bay. Some folks want to, particularly target waters that have low oxygen for their research, or they want to go find a bloom, or teachers want to use this for for classroom exercises, homework problems. Students, PhD students, and master students use our output for a whole slew of different things regarding for their research as well. So we really have a large number of different types of stakeholders that have really driven the development over the years of the forecast system. So now I want to talk a little bit about the actual system. So this will just be a very broad overview, but happy to answer our questions and provide some more detailed afterwards. But this is a ROMS-based estuarine model. Our resolution currently is about 600 meters by 600 meters. We have higher resolution models of some of the tributaries in the York and the James and the Potomac, for instance, but those aren't online in the forecast mode yet. We have 20 depths throughout the bay. We include processes like the tides, wetting, drying, waves, and then we have, in terms of the biogeochemistry, we have nutrients, plankton, um, also a full carbonate chemistry model as well. And in terms of the inputs from the land, we get the river inputs and stream flow from the USGS data, as well as the Bay Program's regulatory watershed model. In terms of the atmospheric forecast, we get these from basically NOAA's weather forecast. So we use winds, temperature, precipitation, solar radiation, all from the NAM model, the North American Mesoscale model. From the coastal inputs, we get that information in terms of the biogeochemistry from climatological data. And then in terms of the physics, we use forecasts from the Rams-Doppio model in the Atlantic. And we have all this written up in a paper here down at the bottom of this, Beaver et al. This is back in 2021, so we've made a lot of updates since then. But that's a good way to learn more about the system for anyone who's interested. And I always want to say that none of this at all would be possible if we didn't have so much data. We are really lucky with how much data we have in the Chesapeake Bay. I work with colleagues that have similar forecasting systems in other places around the world, really, and no one, I must say, is as lucky as we are as to have so much data in the Bay. We've got, we use their cruises about from almost 40 years now, starting in 1985. We have about 17 cruises a year, simultaneous ships, actually, so we can get kind of synoptic feeling of what's going on in the bay. About 100, 150 stations throughout the bay, and they're measuring temperature, salinity, oxygen, pH, and chlorophyll throughout the water column, and then nutrients at a few bottle locations as well. So this is just, we use all of this data to evaluate and calibrate the model with, and continue to update it, the model pretty much once a year. Our forecasts are used primarily during the summer season, so we kind of use the off season, the fall, winter, spring, to make updates to the model, and then run the model through the summer with the updated model each year. So in addition to the cruise data, we also have continuous monitoring data. So from buoys, And this is just an example now of of one of the types of buoys. We have vertical profiles at a number of different locations, each from the spring, summer, fall. This is one from a few years ago and here we're looking at oxygen. So this is most of the buoys just have temperature and salinity, but these new ones have oxygen as well, which is really useful. And we've really learned a lot about the high frequency variability. So before we had these cruises that are every 2 weeks or every 4 weeks. And it turns out that at the bottom, because of the tidal cycling internal waves, you can get the oxygen concentration to vary from almost 7 or 8 milligrams per liter at one point during the day down to like 2 or 3 milligrams per liter. And when you just sample this once a day, it's kind of a crapshoot what you're going to get. So it's great to have this continuous measurements at the bottom and throughout the water column as well. So that's very useful for developing the forecasts. Okay, so we've got the atmospheric inputs, the terrestrial inputs, the coastal inputs. We evaluate the model with all of this in situ data, and then we turn this into a real-time model forecast. So the model runs every night, overnight, automatically, and then in the morning it produces a 5-day forecast. And we show online the forecast for basically the forecast for the given day, tomorrow, and then 5 days out. So today, we'll see today, Tuesday, and then Friday will be online. And we put all of these forecasts on our local VIMS website. So vims.edu/CBEFS. So feel free to bring it up if you have an extra screen and can do that while watching a Zoom. Alternatively, you can also do this on your phone if you you can use the QR code there. So we have this all on our website, but we also have all this information on the IU's Maricus portal, our regional association of the integrated IU's operational observing system. And there, I'm not going to talk about that part today, but there's all of our model forecasts are available there, and you can do an amazing amount of things. You can do animations there, you can zoom in and out, you can compare model and data, all sorts of things, and overlay all different things there. So there's a lot of possibilities there. On the other side, it's a little bit harder to figure out all it can do because there's so many possibilities. Our site is very simple. It basically just has static maps on the VIMS website. So that's what I'm going to be talking about today. So if you use that QR code on your phone, and you're going to see something like this in the center panel. And then this button, I'm assuming you can see my cursor, but there's a button at the bottom with the arrow and the square. That's basically share, right? If you press that, scroll down on an iPhone, I'm sure there's the same way to do it on an Android. You can save it on your home screen, and basically it becomes an app. So if you do that, it's going to look just like this. And then you have basically an app where you can just click on that and you get a forecast whenever you want to see what's going on in the bay. So if you were to do that right now, if you either on a computer laptop or on your phone, you would see scroll and click on oxygen or hypoxia, you'll see a map like this. And so this is what I just downloaded. This is a screenshot of our 5-day forecast. So this is showing what's going to be what the bottom concentrations of oxygen are going to look like on Friday. So here, the blues represent the high bottom oxygen water. So this is the good bottom water for the fish and the crabs. Everyone, they're all happy there. Yellow and green are moderately low oxygen, but you'll still find some fish and crabs there. And then the orange and the red are where the danger zones for the organisms, and basically that's what the watermen call bad water. That's where you will not find fish. Or very happy, not a live fish at all. So right now we're, being in the end of September, the weather out there, oh, it's a beautiful, cool fall day. I'm loving it. And the conditions in the water in the bay are really pretty good. You just see this one little spot in the Potomac that's a little red. So if we look at, for example, what it looked like on July 25th, this is what, it looks like at a a good portion of the summer when the temperatures are really high. So this red area here, this is all what's the basically so-called dead zone. We say so-called because not everything there is dead, but the fish do definitely avoid those areas. You're not going to find much in the way of fish in those areas. They'll swim out of the red zones and actually into the yellow to try to escape, to basically find places where they can breathe better. So that's in terms of maps of oxygen. Um, our stakeholders actually asked also for this kind of visualization. So this is something else we put in a few years ago. Again, this is for the summer because there's no problems out there right now. But at these 4 locations where the circles are, these are the 4 profiles here basically or go along with these 4 circles. So if we look at this top circle here, this site here, uh, this is the profile of oxygen. So the stakeholders are fishermen out there wanted to know how deep can they fish? How deep is the good water that's healthy for the fish? And so basically right here, they can see 12 feet. We always deal in feet because that's what they're asked for. And then at the second location, they can go down to about 18 feet, about 60 feet at this third station. And here where it's gray, they can fish all the way to the bottom. There's no problem at all. So in Virginia waters right now, we don't have much in the way of concerns about low oxygen. But that was a visualization that they specifically asked for in some of our focus work groups with them. So we have oxygen, we went through that. We have a lot of other things on here, and the depth of the oxygen. We have salinity, temperature, acidification metrics, harmful algal blooms, water clarity, waves. So I just thought I would show you go through and show you a few other things, examples of what we have. So here on the left, we have bottom temperature, and then on the right, we have bottom salinity. And so this is again for Friday. So of course, bottom temperature, pretty similar throughout the whole bay. That's pretty typical. We're seeing temperatures in between 70 and 80 degrees in the bottom waters. Generally a little higher in the shallow areas. They've warmed up, a little cooler in the deeper central areas, which take longer to warm. In terms of salinity, of course, the high salinity water from the ocean, you can see out here outside the Chesapeake Bay with the Susquehanna, the Potomac, the Rappahannock, York, and James bringing in the fresh water from those tributaries. We also have pH and saturation state for our aquaculture folks, and also we have some so many of our stakeholders are in the Virginia area. We also have some maps that are zoomed in for these locations. So these are some of the examples of zoomed in maps with pH on the left and aragonite saturation state on the right. So again, you can see the low pH water generally coming in from the rivers, with it being higher background pH in the open bay. Yeah, so those are we have some aquaculture folks in Mobjack Bay around here and the lower Rappahannock that use this information that we provide. Next, we also show that basically the chance of encountering some of these noxious organisms like sea nettles and Vibrio and algal blooms as well. So here, we aren't forecasting the actual concentration of these organisms. We're just forecasting the percent chance of encountering those. So this is kind of like a precipitation forecast. We aren't saying that you may see a rain icon on the day, right, at your house when you look at the forecast in the morning. It's not to say that it's going to be raining 100% of the time when you see that icon. It just says, bring your umbrella, be careful. It could be a rainy day. And that's kind of the way these are. So it's a percent chance. If it gets up to 80-90% chance, it's quite likely. We don't get up that high very often, but occasionally we do. So sea nettles again and Vibrio, not a prime time for these ORHABs right now. But to show you, for example, this algal bloom forecast, this was what it looked like on, again, this July 25th, the hot day in the middle of the summer. So all of this green area, and we have some yellow areas too, right near, I think right near VIMS and right near ODU as well. We've got some yellow high. We had some very high chance, and actually some blooms, high, at least high phytoplankton concentrations observed there as well. And what we have found, we started out by having forecasts of a particular species per centrum minimum. And then after multiple iterations going back and forth with some of our stakeholders, we really found that what they really wanted to know is if there's going to be basically any kind of harmful algae blooming out there. So developed some algorithms based on the chance of 7 most common harmful algal species, and developed the algorithm to predict when we might see high concentrations of those species. So this is not a prediction of any one species, but instead this is a prediction of there being any type of species or a mix of species out there, just some high concentrations of this. And that's really what the fishermen really are concerned about. That they don't want to go, and beachgoers too, really, right? They don't want to go, even if it's not harmful, they don't want to go swim in an algae bloom. So this, we found that it has been pretty useful for a number of people. Another thing we produce are forecasts of wave height. So, and this we provide a few different times a day during the snapshots of various different times. So this is Thursday afternoon's forecast. And here, this is a really common area for high waves off the Potomac. High on Thursday afternoon, and then you can see by Friday afternoon, the prediction is all gone. So those will be much lower waves. As usual, almost always we see higher waves, of course, out in the Atlantic Ocean. One of our newer features are forecasts of marine heat waves. So on the left here, again, this is today's forecast. And yes, we have no forecast of any heat waves today. Very nice and cool day out there. And we've had some cool weather for quite a while now. But on the right here, I'm showing you what it looked like back in May when we had quite some very warm weather. And you can see here the red areas are the locations of the heat waves. And we use the traditional Hobb day definition. So I think it's 5-day forecast, 5 days of temperatures greater than climatology is how that's defined. We also show a number of other things on the website. We show the total number of days in 2025 where the surface marine heat wave was observed, or modeled. So here we have up to 60 to 80 days so far in 2025. So that's quite a few. A few little hot spots here in Mobjack Bay is particularly a lot of heat wave days here. And then on the right panel, it's showing the longest heat wave that we've had at every location throughout the bay. There's actually a number of different definitions of marine heat waves. Some folks, well, basically an alternate NOAA definition that some of the fisheries folks use is just any day with water temperature greater than 82.5 degrees Fahrenheit. And so we had that on there too. Of course, that's not compared to climatology. That's just a flat out greater than 82.5. Things start not doing too well when we get temperatures that high. And as you can see, in July 25th, we had much of the bay experiencing those very high temperatures. So interestingly, we thought one of the things our stakeholders really requested from us was information about how different today would be out if they go out on the water compared to other days in the past on the same date. So basically, what's today, September 22nd, 2025, how different is today going to be compared to the average September 22nd? And it turns out that a lot of these folks on the bay had to keep really good notes on what the conditions have been in past years, so they can actually go back and see what this time of year in the past, where has been a good fishing spot, what has there been a bad bloom, or and these types of things. So they want to know, is today going to be kind of like your typical September 22nd? So basically what this means is a difference from climatology, right? So here on the map on today, we have the bottom temperature looks like this on the left, and on the right is the difference from climatology. So you can see today out there, the ocean water is about 5 degrees or more warmer than usual. So it's the ocean, the coastal ocean is very, very warm. This has been a trend in, or a pattern in recent years. The offshore the Chesapeake Bay mouth has been quite warm, and that's showing that today. And but on the other hand, there's some regions in the middle of the bay that actually are, the bottom temperature is cooler than the average. So yeah, so that's something that they requested that we are able to provide. Another thing that our stakeholders requested was actually how some indication of how well our model was working. So actually this kind of surprised me. I thought they would just kind of take our word for it, but no, they really wanted to see whether the model's working. So what we've done, yeah, tried to really hard to have a lot of model data comparison on the site that folks can look at if they're interested in that kind of thing. So here we've got two buoys. Well, a buoy at Stingray Point, kind of in the middle of the bay, salinity on the left, temperature on the right. Black is the observations, real-time observations from the buoy, and red is the model. So you can see we can log in every morning and make sure that nothing is going completely awry. And you can see we're picking up some of the variability pretty well in terms of temperature. Not too much going on in salinity, but we'll see if we get some blips up here later. This again is the forecast, and of course the observations stop. Yesterday's observations were the last ones to be recorded here. So we've got this at a number of different locations all throughout the bay at all the different buoys. And these are, yeah, updated daily. We also have show comparisons with our continuous vertical profilers. So we've got a few of these throughout the bay, not nearly as many as we would like. Oops. But we do have a few of these. So this is from actually an example from a couple of years ago. I thought it was particularly neat, where you could really see this variability. So here we're looking, this is the depth on the y-axis. On the x-axis is 3 days in July. The top panel is our model results, and the bottom panel is the oxygen data. So you can see that the model's predicting these waves of and this diurnal, or yeah, this variability, I'll just say, of oxygen. And you really see this in the observations as well. So this is where you can see, if you look at the bottom oxygen concentration, it's varying from less than 2 milligrams per liter to 7 or 8 milligrams per liter, all in just a few hours time span. So, you see how hard it is although we have all these cruise data, the results matter are going to vary considerably. If the cruise sampled right here at one of these red points and measured 7 or 8 milligrams per liter at the bottom, considering, or if they measured 6 hours later and they got 1 to 2 milligrams per liter. So this was a really interesting, but look at the high variability of the bottom oxygen concentrations in the bay. But yeah, also helps us show how well the model is reproducing the observations in real time. So we also have model data comparisons on where the data is not in real time. These are the cruises that I talked about before. We are able to get the cruise data within a week or two, which is maybe 2 or 3 now, weeks after they're collected. And we post them as soon as we have them. But you can see that it's a few weeks back. This is from earlier in the spring, but we post them um, on the plot. So here we've got surface temperature on the top and bottom temperature on the bottom panel here. And over on the right, we've got salinity with surface salinity and bottom salinity. The gray lines in each case represent the standard deviation over the 40 years. So you can see sometimes we get, actually a lot of the spring was above this standard deviation of the 40 years for a good part. So we really had a really warm spring. On the other hand, the winter was really cold, and the surface temperature colder than the standard deviation. So that's always interesting to look at. And then here is oxygen. We've got oxygen at a couple different stations in the bay. Same thing here. The black line is the climatological average. Gray lines are the standard deviation. And you can see how variable the oxygen is. The blue is the model results. This is at the surface and the bottom for bottom oxygen and in Maryland. And this is farther south in the bay, again, surface and bottom. So one other thing I wanted to talk a little bit about is our real-time dead zone tracking for the Bay. So we also work with, well, one of the things the Chesapeake Bay coastal resource managers really want to know is has to do with the total amount of volume of hypoxic water in the bay. They want to know whether their nutrient reduction efforts are really having an effect or not. So we have this real-time dead zone tracking online for the summer. And so here we've got the dead zone size in kilometers from May 1st through today, basically, we're here in the middle of September. The dark blue area here is for 2025. You can see it's very low now at the end of the summer. And then these individual lines represent the other years from 2020 to 2024. So we can see how this year is comparing to other years in the recent past. So you can see that actually this year it started quite late, interestingly. But so we thought this was looking really good, but the volume of the total volume of this dead zone or these hypoxic waters reached very high numbers, really high volumes in the middle of July. Before crashing down again. So here, this is often the case when we get a tropical storm coming through. So I think this was Erin here coming through, really mixing up the bay, mixing up those low oxygen waters with a high oxygen surface waters, and that kind of gets rid of most of the hypoxic volume, and it never really came back again. This blue line here, the cyan line, that was last year, and we had another, I forget the name of the storm, but come through very similarly, mix up the bay, and then once again, the hypoxia never really fully established itself afterwards. Other years when we don't have a tropical storm, it kind of it fades out more slowly throughout time. So each fall we put together a dead zone report card. So this is the one that came out at the top, just a little bit of the bit headline of that came out last year in November. We look at a few different metrics each year. So we look at the daily maximum hypoxic volume. So this is the single, how large was that, the size of the dead zone on the maximum on any one given day. We also look at the duration, so how long from start to finish. And then the total annual hypoxic volume, basically the area under the curve. So the cumulative amount of hypoxic volume over the year. And that gives us one number to compare for all the different years. So in 2024, we found that the daily maximum hypoxic volume was greater than most of the years. And the annual hypoxic volume was greater than most of the years, but the duration was less. So very much like this year, it started late, ended early. But the maximum was quite high in July, both this year and last year. So I wanted to, a couple things before I finish up, and then I'm going to show you a little bit of the website, just go through a few things on there. I just wanted to give you a little bit of a timeline. So this has been a long time coming. The forecast system, it's been an effort by a lot of people over a lot of years. It all started with a coastal ocean modeling testbed project that was funded by NOAA in 2013. At that point, we were working with NOAA to try to get operational oxygen forecasts or hypoxia forecasts online in their CBEFS, their official operational forecast system. We got a very simple oxygen model and handed it all over, but never could quite get that working operationally in NOAA. So it has never become an official NOAA forecast. But meanwhile, we decided to kind of go on our own and establish what we consider to be operational because it runs 24/7, 365 days of the year, pretty much. Only if we have major power outages that does present a problem, but generally those don't last for more than a day. Um, and we have spent a lot of time in the subsequent years working with end users, really identifying what they needed, and getting their feedback on our products. We have really added more and more products as time has gone on through 2016. And then eventually we found that our county funding was not renewed by NOAA. This it turned out they wanted to focus on hurricanes. There'd been a lot of hurricanes in the previous year. They wanted to focus on hurricanes instead of hypoxia forecasts. So that was a bummer. But this is when we got some funding to make these dead zone report cards. So we kind of went in another direction. This is also when users were really telling us that they really wanted these forecasts available on smartphones. So we put some effort towards making our forecasts more accessible on phones and mobile friendly devices or mobile devices. Eventually, Maricus, so this our regional IU's association picked up the funding of our forecast. So they provided a bit of forecast and added our forecast to their ocean map portal. Um, and we continued at the same time, also continued to provide our own forecasts. Then through the years, we continued to add other variables. Eventually, the NOAA's ocean acidification program got wind of what we were doing, and we worked with them, and they provided some funding for us to really focus on the aquaculture and shellfish, or shellfish aquaculture and acidification metrics for forecasting those. And that really increased our user base. So that was great to work kind of more on the acidification part for a few years. Eventually, the ComT project, we were funded again on the ComT project, this time for HABs and Vibrio. And that's been going on. That project has just ended. It went on for several years. This is when we added more of the model data comparisons, and we added the water clarity in waves, Vibrio, jellyfish. One of the things that I didn't talk about was that we also added automated alerts. So our stakeholders can ask if anyone wants an automated alert of certain conditions at a certain location in the bay, we can provide that. And that comes as an email alert for whatever condition anyone requests. The next year, we developed again a single species a machine learning algorithm for a single HAB species. But then ultimately, we talked with more work with our stakeholders, really found that they just wanted, instead of individual algorithms for individual forecasts for individual species, they really wanted a general forecast for any HAB. So we kind of went back to the drawing board and worked on that. And that's kind of was how we came about our HAB forecasts that are out there now. Then later, we received some NCOS MERHAB funding, and actually, Marjy Mulholland talked about this project last week, I think, at this seminar series, and Eileen is involved in that as well. So we're working on Marge and Alex forecasts and adding those into the CBEFS, which are particularly useful for our region of the bay, in the lower Chesapeake Bay. Those are the primary HABs that we see around VIMS and around ODU. So those are of particular interest to us. Meanwhile, we did other little things like dramatically increase the resolution of the graphics, so we can really zoom in now easier. And most recently, we've just actually the 5-day forecast that I've showed today has come online this year, so that's new. And now we have a little bit of funding for NOAA's got a new way to apply for funding for a routine product delivery. So it's not really improving a product, but it's just for continuing to put forth the product, just a small amount of funding to keep us going. So we've applied for that and got that funding. So I guess the end of the story is it's been piecemeal, just sticking with it, trying to stick through the dry times, and yeah, and find funding wherever we can. But we've been pretty successful in being able to keep this going throughout the years. So finally, just a few lessons learned. I think it's been really important for us to keep a research version of the model going as well as the forecast version. So we have students work on various different aspects of the model all the time. And so we've got kind of one group, one part of the group is working to improve the model, and another kind of part of the group is working on the forecasts. And this makes sure our forecasts are staying up to date. Um, yeah, and then another thing is that it turns out, with our work with these end users, some of the end users have been with us through the whole time, but their priorities have changed dramatically. One year they'll be totally, concerned about salinity because it's been a huge, um, very very wet year with all the oysters were dying because of too low salinity. And then the next year they're worried about pH, and then the next year, they're worried about HABs because there's a hard log lots of HAB blooms. Right now, we haven't had any HAB blooms, so now they're not worried about HABs right now. So the priorities are always changing of the end users. So we found it's really important to keep talking with them, and learning how their priorities and their needs are changing throughout time. We feel like it's really helpful to have our forecast on two different sites, both on our VIMS site, on the website, very simple, mobile friendly, and then also the Maricruz Oceans map, where you can do a lot more. And science, it's more geared for, I think, for scientists to dig in deeper to do some really neat, fancy visualizations on there. A lot of our users really wanted us to have a one-stop shop. That's why we put waves on there, something everyone going out on the bay wants to know. Definitely multiple different definitions of operational. We feel this is pretty much operational because it's out there, being used, available 24/7. Of course, NOAA has their own definition of that. Um, Definitely a good way to determine who uses this is when our HPC system did go down in the spring for a few days. And yeah, the nice thing was we had learned lots of people were using it because they all wanted to know what happened to our forecasts. And just the last thing here that we're currently thinking about is, although the website really works well and you can download this app to our home screen, we still have folks that are requesting us that we develop this into a real app that they can buy on an app store. So that is something that we're thinking about as well, because folks just keep asking for that. So yeah, so hopefully I've given you a little idea about who's using these forecasts, what's available. And then I thought now I'm going to try to stop sharing this and just go to the website and kind of lead you through just a little bit, to show you what's on there. See if this works. Share. Let's see, I will share this. Yeah. So if you go again to, this is the long the long name, but you can also just go to vims.edu/CBEFS, and you'll get to a page like this. Got a background here, and then all of these different products. So for example, if we go to model data comparisons, we can see the vertical profiles. These are some of the locations that we have these vertical profiles producing data right now. So on the top here is our model estimates. The dashed line is today, September 22nd. After this is our forecast. Of course, the data stop at the dashed line. So we can just keep a general feeling for first of all, whether our sensors are operating well or not, and if the model is generally looking good. If you go down, here's another site. Here you can, we also find, we do see some odd things in the data. You have to take these both with a little bit of a grain of salt. Something odd happened here, with the hypoxic water at the surface. That's definitely not true. And you can see the red line here is the observations and the blue is the data. So you see that their match is pretty good most of the time. Looks like a little bit of sensor drift there, a couple times, but again, you see maybe a little bit more variability in the observations than the data. But generally, this kind of reassures us that the model is generally producing what's out there. And then we can go to temperature. We have the same thing for temperature. So again, here in the top is the model results. Down here is the data. Pretty much available. A few outages, but The comparisons are looking pretty good for the temperature. Um, let's see, what else shall I show? Water level. We also have water level. So here, the shorter time scale. This is today, the blue dashed line here. The black is the observations. It's from Chesapeake, and then the red are the model results in terms of water level. Um, Different. This is water surface elevation. This is trailing average. Um, I forget what WSC stands for, but the model and the data are looking pretty good in comparison. On here we have the focused salinity and temperature forecast. So, for example, here, if you look at salinity in the lower Chesapeake Bay, you can kind of get a closer view of what is happening. This is, again, this is what's going on today in terms of salinity there. This is tomorrow, looks very similar. And then this is Friday. And one of the other things that I didn't show you, but we have always is a trend. So here's the 5-day trend. So you can see that the salinity is definitely increasing on this side of the bay and decreasing on this side of the bay, on the bay mouth. This is often, we often see this depends on a wind pattern, whether one side's increasing and one side's decreasing. But yeah, lots to look at. Boy, when a storm comes through, you can yeah, definitely spend a lot of time looking through all this. In terms of our harmful algal blooms, again, nothing muching out there right now. Percent chance is slightly increasing and decreasing in some areas, but generally very low. Another thing that we have here is the percent of the Chesapeake Bay, a time series over which how much of the bay had a greater than an 80% in blue chance of harmful algal bloom. So you can see back historically, nothing much until June, but this was, at one point about 40-50% of the bay had pretty high likelihood of a harmful algal bloom. But right now, basically not much chance out there right now. Um, yeah, and then I guess water clarity I didn't really mention, but again, that was something that a lot of our fishermen use. So this is, if I scroll down to Friday's forecast, you can see very clear water, of course, offshore. Susquehanna up here, very murky water. Some areas murkier than others. And then again, this is the trend over the 5 days. This is decreasing water clarity over here and increasing in the blue on the western side of the bay. So I think I will end there. Oh yeah, and then to contact me, we have contact information. This is always my email here, always with disclaimers, of course. More information about the model setup, the various different inputs and all. There's more information there about our daily workflow. Um, yeah. So lots of information, and I think I will stop there and see if anyone has any questions.